Hey class, this is a little bit of a review of our last class, and then hopefully we'll move on to some other topics that will allow you to finish the homework assignment. So, going into, if you could take out your packet, pause this until you can find your packet and take it out. I have no extras. I'm going to start printing one for everybody, and I'm going to treat you responsibly like the kinds of people that can hold on to a piece of paper for more than a couple of days. But anyway, so pull this piece of paper out, and you might want to, definitely need a pen. You might need a little piece of scrap paper. And once you get yourself all together, and pause this until you've done that, and then we'll move on. We're going to go to the second page. On the second page, if you remember, I tried to ask you to see if you can figure out how to match these equations to the graphs that we see. Now, that was a little trickier than we expected, and in fact, if we go through the whole chapter, you would have a good understanding of what's the whole section. You'd have a much better understanding of how to match these graphs. Certain things that we have for tools from the past is things like y-intercepts. We also have the idea that if we have a negative exponent, a negative coefficient in front of the term with our largest exponent, that we get a reflection around the x-axis. We can also use the tools of knowing the zeros. That's the place where the graph crosses the x-axis. Also the y-intercepts. So these are things that we can use to try to get a sense for which graph is which. And the other thing too that we're going to be talking about is an idea of what's called end behavior. You'll notice that most of these graphs, if you look at graph A, there's some wiggling that goes on, and I would call that the place where this is the place where a lot of the action is going on in the graph. End behavior is kind of what happens after the wiggle. So for graph A, the end behavior is up and to the right, and the end behavior to the left as we move toward negative numbers on the x-axis, we have the end behavior of the graph going down into the left. Let's talk about some more end behavior. Let's go to graph B. I would say that this is where all the complicated parts of the graph happen. The end behavior for this graph is down and to the left and down and to the right. That's what the graph has after the complicated things happen, what happens to the graph. So let's see if we just get a concept of end behavior again. Here's graph C. Here's where all the wiggling's going on. The end behavior for this graph is up and to the right and up and to the left. Okay, and again, for D, end behavior here's where everything's going on. I was calling it the wiggle in the other class, but beyond the wiggle, we go up and to the left and down to the right. So this concept of end behavior is something that we're going to pick up as another tool to be able to create graphs or in this case, to identify the graphs. The other thing that what I want you to notice is that we have two types of graphs that are being presented here, and these are two new graphs for us. We have dealt with lines or linear functions a lot, and we have dealt with quadratic functions a lot. And if you go up in the hierarchy, the next level in hierarchy, x is, if you remember, x would be y equals x is linear, and this is x to the 1 power. Y equals x squared is a quadratic. So the next two levels up, we get y equals x to the third. This is called a cubic. And if you remember, cube is like meters cubed, centimeters cubed. Anything that has a third power to it has this word cube associated with it. The last thing we have is a little harder name. It's going to be to the 4th power. We call it a quartic. So any equation or any function where the highest exponent is 4 will be a quartic function. Any function where the highest exponent is 3, I got a little too high there, is 3, is going to be called a cubic function. And we already know what a quadratic and a linear function is. In terms of what a cubic function looks like, cubic functions have n behaviors that are opposites. So if you look at this graph here, A, that would be an example of a cubic equation. B, want to guess? This is the other one where quartic equations have n behaviors that are somewhat symmetric. You're down to the right, down to the left. So this is quartic. See if you can tell me what C is. Stay ahead of me here. D, E, cubic, and F will be quartic. So we have two of each here. Quartic, sometimes they look a little bit like a parabola, but oftentimes if you look at graph C, we get kind of a wiggle that makes it look like a W. That's for it's W looking when the coefficient of the cube term of the x to the fourth term is positive. If it's negative, it flips it and it makes it more like an M. So anyway, that's just some information to glean from this exploration one. The exploration I knew was a little bit challenging, but one of these things that we could do a lot better after this section. If you look at the cubic equations, you'll notice that the n behaviors are opposites, and that also you can see that little wiggly space in the middle there, and then we have the n behavior. So typically with a cubic, we have a bump up, an up bump, and a down bump. So let's go ahead and from the old days here, let's go ahead and look at E right here. E would be considered increasing from, increasing for x values that are less than 0, and then increasing for x values greater than 0. I'm not sure exactly what's going on in that wiggle, so that may not be as accurate as I want it to be. But anyway, reading from left to right, you can see that this graph is going down when it gets to 0. So we'll say that this graph is decreasing for values less than x equals 0 and increasing for x values greater than 0. So these are concepts that we're going to have to practice to get good at. But let's moving to the next page. Some terms to remember is as you see in the table here is that we have constant functions, linear functions. These are things that we've already dealt with, and our new things are the third degree functions and the fourth degree functions. Third degree being the cubic equations and the quartic being the fourth power. So examples I think are a little bit easier to understand if you see them over here. Going to example 1, identify the polynomial functions. We did this in class. Just a reminder that a polynomial function has to have exponents that are whole numbers. So whole number exponents. And so if we look at A, we'll notice that we don't have an exponent here for the 5x, but it's x to the 1. And if you wish, this is 8x to the 0. But 3, 1, and 0 are all whole numbers. So this is a polynomial function. Is it in standard form is the next question. Yes, it is in standard form. Standard form means that the exponents go in decreasing order of size. So we got x to the third, x to the 1, x to the 0. So the bigger exponents to the front, and then in numerical order going downward. Is B a function? Well, you might think that it's not a function because of this x squared, this square root at 2 term, but that's fine. Why? Because all the exponents are whole numbers. All right, so this is a function. Unfortunately, this one is not in standard form. To put this one in standard form, I will need to do the following. I'll need to move this term to the front. So g of x equals root 2 x to the fourth minus 0.8 x to the third minus 12x, and we're done. Oh, that's x to the 1. I am so sorry. There you go. Oh no, that is x to the 0. I wrote that on. Okay. Shoot. Anyway, so let me erase that x because it looks like I just made a mistake. Just 12. Thank you. Now the next two functions, c and d. I mean, they're not functions actually. Why is this one not? Well, the negative 1. All right, the negative 1 is not a whole number. A whole number is are all positive, and let's go to g. The reason we have a problem here is because an exponent of x is not a whole number, so neither of these are polynomial functions. Moving to and go ahead and take a look at a graph. Back to the next page. This is where we have a starting with example 2. One of the things that we can do is use our calculators to plug in to evaluate these to evaluate this function at 3, but we can also do it manually. So in this case, f of 3 is equal to 2 times 3 to the fourth minus 8x squared, sorry about that, 3 squared plus 5 times 3 minus 7 and if you're fortunate to do that all correct, you're going to get 2 times 3 to the fourth. 3 to the fourth is 81 times 2 is 162. 3 squared is 9. 9 times 8 is minus 72. Plus 15 minus 7. Altogether comes out to 98. So that's one way to do that. The other way, if you remember, is that we can put this into the y1 part of our calculator, and then what we could do is retrieve. We could plug in by going to the variables button on your calculator. You go to the vars. You go to where it says vars, and push that button, and then what you're going to do is arrow over to y vars variables, and then you'll see a selection for selection 1 is functions, and when you click on that, you'll see the y1 variable. You click that, and it's going to go right to your screen, and if you put it, whatever number you put in parentheses after that, say in this case 3, will be plugged into the function. So I'm just trying to remind you that that was not meant to be a first time understanding of that. So next is our next topic. In other words, this is a tool that we'll use to try to understand the graphs, is this thing called end behavior. And as I said before, the end behavior is what happens after all that wiggling in the middle. So when we talk about a odd, this is a cubic function that's being drawn right here, with a positive coefficient in the front of the x cubed term, and whenever the coefficient with the number before the x cubed is positive, we would expect that as we have larger values of x as we move to the right, toward infinity, we're going to find that the y values get higher and higher and higher. So that's basically upper left. It's going up to the left, up to the right. Sorry. With y equals x cubed to the left, if we're going to go toward negative numbers, so as x goes to negative infinity, so we go really, really, really far to the left, we'll find that the y values get consistently larger in the negative direction. So the end behavior here is down and to the left. So we can go through this whole thing. I think it would drive you crazy, but this next one is related to the idea of a negative coefficient for a cubic equation. And in that case, what happens, remember, is a negative always flips the function. So if it flips the function, the end behavior will become flipped. So instead of going down to the left, it's going to go up. It's going to go up to the left and then down to the right on the other side. So anyway, the key is end behavior is what happens to the function after the wiggling is done, and it helps us understand how the function is going to be drawn, and we'll go into that a little bit later. Now let's apply this concept of end behavior to an actual function. So let's look at this example 3. And the idea is, let's just describe the end behavior of the following function. The end behavior of any function is going to be determined by the first term of the function when it's in standard form. So in this case, the negative 0.5 x to the fourth is what's going to determine the end behavior. And again, the end behavior can only be one of 4 things: up to the right, up to the left, down to the right, down to the left. So let's get a sense for what's going on here. If I take the question is here, what happens when on a graph, what's going to happen to this function as we move to increasingly negative values of x? So the idea is, let's see what happens when we put in, maybe not the number infinity because it's not a number, but let's just put a big number in and get a sense for what's happening to the y value. So let's say I plug in negative 1,000 for x for the first term. I'll get negative 0.5 times negative 1,000, not infinity, but a big number nonetheless, to the fourth. So we're just going to focus on that first term. If I take a negative number and I bring it to the fourth power, negative times negative is positive, times a negative is negative, times a negative again is a positive. So this number here becomes very positive, but then again, in the end, we have to multiply it by the 0.5, which is a negative. So this means that as we move to the left toward a negative infinity, that the graph is moving downward, increasingly more negative. So this function's end behavior is to the left is going to be down and to the left. Let's figure out what it's going to be when we move to the right. In other words, we're going to move toward positive infinity. Let's take a big number like 1,000, positive 1,000. Positive 1,000 to the fourth is also going to be a positive, but then again, that negative coefficient is going to be there too. Negative times a positive means that the y values are becoming very, very increasingly more negative. So as we move to the right, we will go, the y values will be going in the negative direction. So that's going to be down and to the right. So the end behavior for this example 3, the end behavior of this graph is going to be down and to the left and down to the right. So, and again, that just gives us one little idea of what's going on. We could also find the y-intercept and maybe find another piece of information to help us draw this graph. But in terms of end behavior, that's it. Again, let's review. The end behavior is going to be determined by the first term in the function. And what we're going to do is we can plug in or consider what happens as we move to the right toward increasingly large values of x, or to the left to plugging in very large values of negative values of x. to see what's going to happen to the graph. So we can plug in values. Later on, you will find after you've done enough of these that you will not need to to plug in a big number. You'll be able to determine it rather quickly just by sight. So let's move to the next page. Move toward look at that's when we have. In the next page, we're going to be graphing polynomial functions. So we're going to use the end behavior for here, and we're also going to use we'll also use a technique that we've probably used all the way from middle school. We're going to graph a few points, and once we understand the end behavior and we graph a few points, we may be able to trace out the graph. Now, please understand that you're not going to be able to graph this thing perfectly. And so we're just going to kind of, we're going to get an approximation for what the graph's going to look like. So to do that, what we're going to do is we're going to make a chart in XY T chart, and we're going to plug in the old values 2, 1, 0, -1, -2. My recommendation would be to put this function into the calculator as y1, and then go ahead and use that vars function to be able to plug in the different values. It's going to save you a lot of time. There's one other method that we can do using the table, but anyway, I did that, and the numbers I get, well, actually my class did this, is 2. When I plug in 2, I get -1. You could do that by hand, and this one's a little easier. When you plug in 1, you get 0. At 0, plugging in 0 gives me -3. And plugging in -1 gives me, let me see, I got -4. And finally, -2 gives me a 3, +3. So I'm going to graph these 3 points, and then let's and then we're going to talk about the end behaviors. So 2, -1, 0, 1, 0, 0, -3, -1, -4, -2, 3. Things look like they're all over the place. So again, let's go ahead and consider the end behavior. And let's go first, let's talk about what happens when we have big negative values. So let me go ahead and use my hypothetical negative 1,000 thing. -1,000 to the third is a negative times a negative times a negative, which is a negative. And then there's a negative outside here, so a negative times a negative is going to be a positive. So this means as I move to the left, I'm going to go to positive values of y, which is this direction. So the end behavior is up to the left. On the other side of the function, as I move to the right, I would do -1,000, positive 1,000 to the third. Well, positive 1,000 to the third is going to be positive times the negative, and that's going to be negative. So that means as I move, as I move toward positive infinity, my y value is going to be increasingly negative, and so the end behavior is going to be down. So that's what I know the graph's going to look like. Now, if you remember the cubic equation, if you go back a few pages, let me move toward there. So let's consider how we're going to do this end behavior. My feeling is that this is where the graph goes up, and we need 2 bumps. There's the down bump and the up bump, and then we go end behavior down and to the right. So I have to make sure that I have it goes up to the left and down to the right, and that it connects these points. Again, because it's cubic, I'm going to expect what we call a local minimum. That's what this is called. And a local maximum. It's kind of like with the parabola, we either had a maximum or a minimum. With a cubic, we get both. That's why they call it relative minimum and relative maximum. Okay, let's look at this quartic. Here's a quartic, another one to graph. Again, we're going to go ahead and hope that the math teachers that put this thing together gave us some good numbers here to deal with, so that all the wiggling goes on. We're going to say, oh, that wiggling is going to go on near the origin. So it's the values I have for this is going to be -4, 0, 4, 2, 12. Again, I plug that into my calculator, and I use my calculator to be able to calculate those values. Let me go ahead and graph them. Get 2, -4, 1, 0, 0, 4, -1, 2, -2, 12, way up here somewhere. I'll just put it up there. Anyway, the end behavior is going to be given by the x to the fourth. So if x to the fourth is a really big negative, we're going to get a positive. If x to the 4 is a really big positive, we get a positive. So that means that the end behavior going, if we move to the left toward infinity, we're going to find that the y values are going to be positive. As we go to the right, the y values will also be positive. And this is consistent with what we call an even function. Even function, because the exponent is 4, is that we have that symmetric end function. But in this one, what we need to do is we need to produce that little W shape that is characteristic of the quartic functions. I'm going to predict that this is the place where the end behavior happens in the upper left direction, and this is going to be a local minimum, up, down, and up. Now that might take a while for you to figure out, but again, we know that the quartic function is going to have, it's either going to look W-ish or M-ish. And so using that understanding and the end and those points and the end, the end characteristics, you'll be able to figure this thing out. Now, if I put this graph on the calculator, it should be relatively similar. Okay, now let's move to the last piece, and this is from the perspective of looking at the graph from left to right. So let's go ahead here. What's going to be critical to understand the last 4 questions is what this is going to give us is it's going to give us enough information, believe it or not, to sketch a graph. The information is given in these inequalities that you're seeing here, and I want to remind you that at one point we used to call this between notation when you have the inequalities, both of them pointing to the left, and with the smaller number to the left and the bigger number to the right. This means everything between, that's my dog, between 0 and 4. All right. These two terms here are best are saying, one, f of x is greater than 0. That's basically saying it's above the x-axis. This conversely would say below the x-axis. Okay, so let's make sure we understand that stuff first. So, in addition, it's important to understand that when we talk about increasing, we're talking about, you're going to get these little hints. So what I wanted to do first is to deal with the increasing decreasing part separately. So f is increasing for, if you look at the first line here, right? F is increasing when x is less than 0. So that's saying x less than 0 is over here, right? And so we're going to say that for numbers less than 0, we're going to be going up. The next one, let me erase my little mess here. It also says that it's increasing for values of x greater than 4. So let me write that. So from 4, it's going to be increasing for numbers greater than 4. The next thing, it says that f decreases between 0 and 4. So it's decreasing from 0 up here to 4. Okay, so these lines are not the graph. And maybe I should just go ahead and change the colors. And I'll change to blue for the actual graph. Now this is where things get helpful. When we go down here, and it says for above the x-axis, x is greater than 0. Above the function is above the x-axis from between -2 and +3. From -2 to +3, the graph is above the x-axis. So we know that this is less than 0, therefore it must be going up. It's increasing in this area until we get to the y-axis, and then at 0 it decreases and to here. So we know that we got something like this happening. Let's go to the next topic here. And you guys must be ready to shoot me at this point. But anyway, I don't blame you. Now it says it's also increasing. It's also above the x-axis for x values greater than 5. So this is 5. So we know that it's going to go increasing because our little black line indicates that it's increasing. Okay, so that is what we see above the x-axis. Let's talk about what's going on below the x-axis when f of x is less than 0. Well, when f of x is less than 0, x is less than negative. It's less than 0 for all values of x less than -2. Okay, so that's what this means. Now it's interesting because notice that it is also increasing all the way, just like it said, it's increasing for all values of x that are less than 0. The other thing it says is that between 3 and 5, it's also below the x-axis. Well, that must mean that we're doing something like this. Now remember, it goes from decreasing at 4 to increasing at 4. So this must be the place where it rounds around. So there we go. We can get rid of this line. I shouldn't have wrote that, but because I had that as a black line, that was just an indicator of direction. So the blue graph is really the graph itself. So anyway, that was pretty nasty. There's a couple problems like this on the homework. So some of the homework questions look like this. So let's just go ahead and do a quick sketch of 38. See if you can catch on. Clearly, this is one of those things that you have to try a few times before it makes a little bit more sense. But let's go to, it looks like we have numbers between, let's just go 1, 2, 3, 4 in all these directions. And let's work. So the first part is going to talk about the increasing and decreasing areas. So let's go ahead and get our little black arrows going. You might want to use a different color. Well, actually, you're not going to be doing these by hand. So F is increasing. This means, again, when we have this notation, it's between -2 and 3. So here's -2, and 3 is over here. And we know that from -2 to 3, we're going to get some kind of an increase. The graph will be going up. And it's decreasing for x less than negative 2. So less than negative 2 will be here. All right. So it's decreasing in that area left of negative 2. And then it's also going to be decreasing for x values bigger than 3. So it's going to decrease for values of bigger than 3. So it's going to go down at 3. So this graph is going to go down, up, down. So let's see what parts are above and what parts are below the graph. So if you remember, this is saying f of x is greater than 0. That's y's. The y values are bigger than 0. This is above the x-axis. So above the x-axis, it's going to be above the x-axis when for x values less than negative 4. So here's negative 4. And for x values less than negative 4, this thing should be, we should have a graph going down. Right? Because we're decreasing. So this is, oh, I told you I'd change the colors, right? Sorry. Let me change the color. So now, okay, now I'm going to be drawing the graph. So here's negative 4. We know it must be decreasing because we're in the area of decreasing. And we'll stop right there. It's above the x-axis. Where else is it above the x-axis? It's above the x-axis between 1 and 5. Between 1 and 5. So here's 1 and 5, I guess, is going to be here. It's above the x-axis, so we know that it's got to go up in this direction. And then when it gets to the 3, it needs to start going down. Whew, okay, and so that's all the stuff above the x-axis. You might be able to infer what's going to happen next. I might think that it's going to be, to connect these lines, I'd have to do something like this and something like this. Let's see if that's what's going to happen. It looks like a cubic equation. So let's go here. This is going to say this is where the graph is below the x-axis. It's below between negative 4 and 1. Negative 4 and 1, just like it seems, right? And then it's also below the x-axis for x values greater than 5. Well, there it is. So this is a sketch, certainly not a very pretty sketch, but this is what our expectation would be of this graph. Now, on the homework, you merely need to match the correct response. But I think the best thing you could do is to try to graph these and just make a rough sketch of what's going on. All right. So is this easy? No. But you have about 3 or 4 to practice on, and hopefully that'll kind of smack it down for you a little bit so that when you get to the quiz you can do one of these things. Okay, so last thing, the real life problem. I did not is something that I'm going to do with you guys when we meet again on Monday to do some applications, but we don't have any applications on the homework, so I'm going to hold off for now and just not have you do any of these problem-solving questions yet. So your homework is everything that I just described. It's going to be called HW 4.1A, and it's on Big Ideas, Math. And you realize that some of you have already started this thing, and but you now have until Monday to finish it. If you ran out of submissions on any of these things, I think that prior to today, trying to get the homework done before you found out that it was extended, then I'm pretty sure that that's not going to be the case with many of you guys in the F period class. But if that is the case, then you can come to see me on Monday during class and show me the work that you did by hand, verify that you understood the question, and I can award you points in that respect. So anyway, for those of you that are in F period and this is a Friday, what I'd invite you to do right now is to do this homework. Now that you're together, you're there, you have the support of your class to do that and to finish it before the end of the period. And I think you should be fine. Anyway, great talking to you guys. Hope this made sense, and I will see you on Monday. So take care now.